So folks, just as you were able to work with lines long before you ever learned to work with vectors, we could also do the same thing with planes. We can learn how to work with planes without using vectors. Let's go ahead and define what we mean by a plane in the traditional sense before we move into looking at how we work with vectors. So a linear equation in R3 is one that can be written in the form ax plus by plus cz plus d equals 0, where a, b, and c are not all 0. So the graph of such a linear equation in R3 is called a plane. So let me give you an example of what we mean by this. Here I can give you 3 distinct points, and we can go ahead and find the corresponding equation of the plane that these 3 points pass through. So I'm going to go ahead and pull that up for you. And I don't think it's essential that you work through this example, but I want you to have a sense of what we're doing. I could go ahead and take that first point, which is the order triplet, 1, 1, 1, and I take my generic plane equation. Everywhere I see an x, I plug in 1. Where I see a y, I plug in 1. And where I see a z, I plug in 1. And that's what I've done there. This equation then simplifies to this equation right here, which I'll call equation 1. Then I can take my second point, which is the order triplet 2, 0, negative 2, and I plug all 3 of those points into the original equation. So we've got 2a. So again, I replace the x value with 2. I replace the y value with 0, and the z value, with negative 2. I plug that into the equation, and we ended up with this second equation. If I do the same thing with the third point here, I take this order triplet. Everywhere I see an x, I replace it with a 1. Everywhere I see a y, I replace it with a 0. Everywhere I see a z, I replace it with a 3. This gives me a third equation here. So what we need to do then is to solve these 3 equations simultaneously. And we could go ahead and do so. And I plug them into a equation solver. You could have worked it by hand. And we found that d it could be any real number. It's called a free variable. And then we could solve for c, b, and a all in terms of d. So then once I pick a number for the variable d, then I can go ahead and find corresponding a, b, and c. And from there, we found that a was negative 5, b was negative 2, c was negative 1. So this is one way to write the equation of the plane, although oftentimes we'll take that constant 8 over to the other side. And in this case, I also divide it by a negative number to give me this other version of the plane. I hope that you've done something like this. Well, maybe you didn't think about solving the equation of a plane. I hope that you've done something like this in your math career where you've solved 3 linear equations. Here was the first one, second one, third one, with 3 unknowns, or in this case 4 unknowns, and we were able to represent everything in terms of one of those unknowns, in this case d. So we are not going to be doing this much in this class, and if we return to our handout, the above method is feasible using your algebra skills, but I think it's challenging and it's hard to keep everything organized. And so better yet, in a linear algebra course, you'll learn a very methodical way of working through that. So what we'd like to do is instead build the same equation of a plane, but we want to do so using vectors instead. So scrolling down. Let's go ahead and just look at a plane, and I think we have, maybe kind of an intuitive sense of what a plane should look like. There's our plane right there, and let's think about how we could think about this plane in terms of vectors. Well, similar to what we did with our line, we could go ahead and think of a plane as a collection of points, and for each one of those points, we could go ahead and draw a corresponding position vector. And so I've got this collection of points here. Each of these tips of these arrows is what forms the plane. Well, it turns out that although this way would work, it's not the best. Similar to how we did with our lines, we want to go ahead and modify this. So what I could do instead is think about taking some common point in this plane, maybe this point right here, and coming up with vectors who also have their tips. They have their tail at this common point that's in the green plane. That's kind of hard to see from my drawing, but this blue point right here is in the green plane. And all of the blue vectors that I'm drawing lie inside of my plane, and notice that their tips are also at the tips of these red vectors. So this turns out to be a better working definition for a plane. So let's go ahead and clean that up a little bit. So now what we're going to say is that a plane could be thought of as a collection of vectors that all share a common tail point, and all of the tips of those vectors, provided they're laid out correctly, I'll show you what I mean by that. All of those tips of those vectors give you the points. So each of these tips gives you the points that lie inside that plane. Well, I want to point out that I don't want just any vector who has its tail right here. This isn't a perfect drawing, but let's say I drew this vector right here. Notice this vector right here, this does not have its tip in the plane, so I don't want that vector. So I need to say something about all of these blue vectors. And let me go ahead and color code this one to clarify. Let's make this yellow. I need to say something that allows me to say I want to keep all of these blue vectors. They all have their common tail at this point. But I don't want this yellow vector, even though it also has a common tail at this point. And this is hard for my picture. It's hard for me to sketch 3 dimensions here, but maybe you could see that this vector, yellow vector, is pointing downwards below the plane. It's exiting the plane, pointing downwards. Whereas all of these blue vectors here lie inside the plane. So the common thing that we're going to notice is that all of these blue vectors inside the plane are going to be perpendicular to the same vector. And that's our final, back up there, that's our final notion that we need in order to finish building out the equation of this plane. And forgive me, folks, I'm working on my school computer, and they sort of chinced on it, so I apologize for the lag. So if we take this common point here, and we take the collection of all those vectors, these are the vectors we want, we need to come up with something that ensures that we do not include this yellow vector right here, even though all these vectors have a common tail all at this point. And the idea to observe is that all vectors in a plane will always be orthogonal to some other vector. Or actually any scalar multiple of this red vector that I just drew, all of the blue vectors in the plane are orthogonal to it. So folks, we're going to give this vector right here, a special name, and we're going to call it the normal vector to the plane. Oftentimes in math, the word normal refers to orthogonality in some sort of way. And what we can see here is that this red vector that I drew here is perpendicular to all of these other blue vectors that lie inside the plane. So careful, the normal vector is an important part of the plane to discuss, but it's important to realize that the red normal vector that I drew here doesn't lie inside of the plane. Rather, it gives me a sense of, almost like just with lines, it gives me sort of a sense of direction that the plane is pointing in. All of the blue vectors that lie in this plane are orthogonal to this red vector here, and so in a sense it gives us direction. So let's go ahead and give this new definition. A plane is a collection of all vectors, all with a tail at some point, maybe we call that point P naught, orthogonal to some other vector called the plane's normal vector. That's our definition of a plane. So we'll go ahead and do this a little more abstractly first, because there's actually nothing in here, even though I drew a picture in 3 dimensions. There's nothing in here that forces me to continue to remain in 3 dimensions. We're still going to have a plane, and we're still going to have a collection of vectors with a common tail, and we're still going to have a normal vector. So we're going to call any of these objects, whether it's a plane or a plane living in a higher dimension, we'll go ahead and call it a hyperplane. And how did we get there? Well, let's take this idea that this hyperplane would be a collection of all vectors whose tail is at some point P naught. So I'm going to construct a bunch of vectors that look like P naught to P. Remember, those are vectors whose tip lies at point P, but who all will share the common tail P naught. Okay? And we want these vectors to be orthogonal to the normal vector. So this actually gives me, this definition gives me an equation that when I solve for that equation or plug in the values for that equation, I'll have the equation for that hyperplane. So I want my vectors in the plane. So this is the vectors in the plane, p naught comma p. So let me go ahead and draw that picture up here with this. So for example, this might be my common point right here. That's not a vector, folks. That's just a direct. That's just me pointing at this p naught. There's that point right there, and then maybe I've got this point. This point right here in the plane that you could call P. So if we wanted to describe this particular blue vector right here, we would say that this particular vector is the vector P naught to P with that arrow. So there's the tail of the vector, there's its tip, and then we show that it's a vector by putting the arrow up above there. So folks, that's our definition of a hyperplane, where we want to take that collection of vectors and ensure that they are orthogonal to a normal vector. Well, how do we ensure orthogonality? Two vectors, just any two vectors, u and v, are orthogonal if what? Their dot product is 0. So I've got these two vectors here, my normal vector and this vector here that's supposed to lie in the plane. P is a point in the plane. P naught is that common tail that lies in the point that's a common tail that lies in the plane. And we want these two vectors to be orthogonal, so we want to force their dot product to be 0. Careful, folks, there's a lot of abstraction here. I want to make sure this makes sense. So keep in mind that this is the number 0 because it's the result of having done a dot product. This is not the 0 vector here. This is the result of doing the dot product. Okay, so let's work a couple of quick examples. Here I'm asking you to find an equation of the hyperplane passing through the point 1, 2, 3, 4 and having a normal vector negative 2, 0, 1, 5. Now, I can't actually draw this hyperplane because it lives in what space? This lives in R4. These are my four-dimensional vectors. I can't draw it, but I still have a point that lives in that space, and I want to talk about a plane, a particular plane, passing through it. Okay? Well, how do we come up with the equation of that hyperplane? Well, this is our idea. We want to take the collection of points who have a tail at 1, 2, 3, 4, and form a vector with that tail so that that vector is orthogonal with our normal vector. So let's let P equal the ordered pair, or the ordered tuple x, y, z, then sometimes we'll use w. We could actually start numbering these variables, but we'll just go ahead and do that for now. We've got these, the four coordinates of this point that lives in, of some arbitrary point living in R4. Okay, so let's let that point be an arbitrary point. Then so that vector, let's construct a vector with that has a tail at the point 1, 2, 3, 4 and a tip at x, y, z, w. So the vector whose tail is at 1, 2, 3, 4 and whose tip is at x, y, z, w would be this vector right here, p naught p. That's what we were talking about here. And that would be the vector. So let's see here. If we go ahead and take the tip point minus the tail point, this would be the vector x minus 1, y minus 2, z minus 3, w minus 4. There I've constructed this abstract vector. This is any vector in R4 whose tail is at the point 1, 2, 3, 4, and whose coordinate, the coordinates of the tip may lie anywhere in R4. But I don't just want any vector in R4. What do I want? So going back to our picture up here that kind of guides us through this, I don't want all vectors in the space that I'm working with. I only want the vectors that lie in a certain plane. Put another way, I don't want this yellow vector. I just want this collection of blue vectors. So what do I need to ensure to make sure that I only take the vectors that lie in the plane? Well, I need these vectors, p naught to p, those vectors, I need them to be orthogonal to my normal vector. So we're going to set up the equation right here. N dot P naught P needs to equal 0. And so we're going to take the normal vector, negative 2, 0, 1, 5, and we're going to dot it with this abstract vector, x minus 1, y minus 2, z minus 3, w minus 4. Now this dot product could come out to be anything if I just chose any x, y, z, w in R4, just taking any abstract point in this space. This dot product could come out to be anything, but I want to force it to come out to be 0. If I force it to come out to be 0, then I'm ensuring that the normal vector here, n, this is my normal vector, I'm ensuring that it's orthogonal to this particular vector. Okay. The last thing we have to do, in fact, I actually like this as a solution. To me, when I see this, this looks like the equation of a plane because it satisfies this definition here. But if we wanted to write it as a more traditional equation, all we have to do is just perform the dot product operation. Remember how we perform the dot product? We take and multiply the coordinates of each of the vectors and then sum them up. So the first coordinate of the first vector is negative 2, and we're going to multiply that to the first coordinate of that second vector, so that would just be x minus 1. Then we're going to add that to 0 times y minus 2. Do I have enough room here? Not really. Plus 1 times z minus 3. That should be a z. 1 times z minus 3. And then we're going to add that to 5 times w minus 4. That's how we would perform this dot product on the left here, and we want to force it to be 0. So this is another form of the equation of this hyperplane. Okay, that was pretty abstract. I'd like to bring it down to be a little bit more concrete here. So when we're dealing with this definition here, if we're in R3, we're just going to call it, instead of a hyperplane, we'll just call it a plane. And let's go ahead and answer this last question for this video. So we want to find the equation of the plane that passes through this point right here with a normal vector of 1, 2, 4. Now, it is not essential that you draw an accurate picture for this problem, but I do think that it is helpful to give yourself a brief little sketch. So I'll go ahead and plot the point negative 2, 5, 1. That would be this point right here. There's the ordered triplet, 2, 5, 1. Okay. And what we want to do is we want to come up with the plane that passes through that point. Now, there actually could be infinitely many planes passing through this point. There are. Don't draw this, folks, because I'm going to erase it. There's one plane, and maybe there's another plane, and maybe there's another plane, and you could imagine all of them passing through that point. But we only want one of these planes. We want the plane that will have a particular normal vector. We want it to have this normal vector, and we think of that as sort of pointing in the direction, giving a sort of sense of direction to the plane. So that vector, let's see here, the vector 1, 2, 4, maybe it points out sort of like that. That will be the normal vector that I want, and so my plane is going to be the collection of all points that lie inside there, which is the collection of all vectors who have a common tail at this point right here, the point 2, 5, 1, a tip somewhere in that plane, and to ensure that this blue vector, each of these blue vectors is actually in the plane, I need each of the blue vectors to all be orthogonal to this yellow normal vector. Okay, so we're going to take x, y, z as just some arbitrary point in space, x, y, z. So let's let p equal x, y, z. So that could be any point in space, but I want to ensure that it actually ends up being on my plane. How do I do that? The first thing I do is I construct a vector with it. So let's construct the vector p naught p. So how do we do that? This is a vector whose tip needs to lie at x, y, z, and whose tail needs to lie at p naught. So that would be the vector x minus 2, y minus 5, z minus 1. So that's this. This is going to stand for some arbitrary vector in this space. All we've said about this vector is that it has to have a tail at 2, 5, 1. At this point, even though this won't be correct, at this point we could be talking about, say, maybe this green vector that's pointing way out of the plane here. It's not in this the original plane that I've drawn. I could be talking about this plane, or this vector right here. How come? because this vector, it just has an arbitrary point, coordinates x, y, z, and it has a tail at that point. I want to make sure that I exclude that vector, but include all of the blue vectors. So what do? I dot this abstract vector with the normal vector and force the outcome to be 0. So let's go ahead and do so. So folks, we'll just take this normal vector, which is 1, 2, 4. We're going to dot it with our arbitrary vector. The only thing that's specified about this arbitrary vector is that it has to have a tail at 1, 5, 2. Now, I could always do this, right? I could always take whatever, even this green vector, I could take this green vector and dot it with this yellow normal vector, but I want to force it to come out to be orthogonal, so I set the dot product to be 0. So let's go ahead and do this. We'll take 1 times x minus 2 plus 2 times y minus 5 plus 4 times z minus 1. This needs to equal 0. I could park my answer here, and I'm actually happy. If I ask you for an equation of plane, you could park your answer here. You could park your answer here, or you could actually expand everything out here, and I'm going to do that. So if I distribute this 1 through, we would have x minus 2. If I distribute this 2 through, we'd have plus 2y minus 10. And if I distribute this 4 through, we'd have plus 4z minus 4, and this has to equal 0. If I collect like terms over to one side, we would have x plus 2y plus 4z. And there we'd have minus 12. That would be minus 16, I believe. Let's see, minus 2, minus 10 is minus 12, minus 16, yes. And if we add it over, we get 16. And this is the more traditional way of seeing the equation of a plane that we came up with. But notice we did it in terms of vectors initially. Folks, this was a tough video, I think. We're going to get better at planes in class, but I needed to get through these examples here with you. Whenever you find, because as we continue in this class, planes won't go anywhere. Whenever you find yourself struggling with planes, please return to this video right here, which gives you the first overview of planes, then this very abstract definition of what a plane is. To me, this definition right here feels very abstract. But then we've worked 2 concrete examples where we've actually computed equations of either planes or hyperplanes. And that's what I want you to take from this video. But if you're feeling a little bit overwhelmed with this, don't worry. We will deal with this some more in class and hopefully get a little more comfortable. Thank you.